Okay, so let's continue on with our discussion about cell respiration and look at a chart that gives us some more information and some numbers that we're kind of concerned with, because the whole purpose of cell respiration is to give us quite a bit of ATP from our glucose. That's the reason we eat glucose. Main reason we physiologically eat it is so we can have a lot of ATP. Now, notice we got different amounts of ATP shown in different parts of the pictures. So we're going to go ahead and have a review over what's happening, and then we will tie it into the final purpose of our ATP at the end. But the first thing is, remember, we divided this up into basically 4 steps. Now, in this particular chart, the steps are still glycolysis, which we see here, and we see that it's occurring in the cytoplasm, which means it's outside of the mitochondria. The second step, which they don't name here, but they show it basically with this block 2-pyruvate move into the mitochondria, and we remove carbon dioxide from it, and that's where we get our acetyl. Then that step is the preparatory or transition reaction. Then the third step is, what do we do with that acetyl once we are inside past both membranes of the mitochondria? And we go through what's called the Krebs cycle or the citric acid cycle. Now, since we're not a biochem class, I'm going to skip all the chemical reactions that occur there and talk about what are our outcomes, though, because the outcomes really what we're interested in here. So again, we're at step 3 now, the citric acid cycle, the Krebs cycle, and what we're doing, we're taking a 2-carbon product called acetyl. We're joining it with an enzyme called coenzyme A. Then we end up with something called acetyl coenzyme A, or acetyl-CoA. And of course, we have 2 of those doing this, but we're looking at what's going on with both of them because they were derived from the pyruvate. The pyruvate was derived from the breakdown of the glucose. Now, we did, in the glycolysis, which again occurred in the cytoplasm, we did make a net gain of 2 ATP. We really made 4 ATP, but it took 2 ATP to begin with, so we had to pay back 2, so we get a net gain of 2. Now, in our, notice what else did we get? Well, we had to pull some hydrogens out of this to get 2 NADHs. That was something that we can, for our short-term nickname, call NAD+. By pulling some hydrogens out, we converted it to NADH, and now we're going to take the hydrogens to the last step in a process called oxidative phosphorylation, but in an area called the electron transport chain. We will get to that and show another PowerPoint and a discussion on what's actually happening here, but let's build to that. All right, so that was our first step. We got 2 ATP, we got 2 NADHs. Second step, no ATP, but we did get 2 more NADHs, because when we were converting pyruvate to acetyl, we pulled carbon dioxides out of it, but we also pulled hydrogens out of it. Okay, so then we go through this biochemical pathway called the Krebs cycle, where we take a 2-carbon, we add it to a 4-carbon product. We go through several steps, and in those several steps, we actually pull out more carbon dioxide. So when you exhale carbon dioxide, you're getting it from this step here, the second step, the preparatory reaction, and you're getting it from the Krebs cycle or citric acid cycle. So when you're exhaling it, that's where it's coming from, and it originally came from the glucose. All right, now, but what else is going on here in this step? Well, we're producing 2 more ATP, so far we got 2 ATP from this step. If pyruvate went in instead of staying out and turning into lactic acid and goes through this, we actually get 2 more ATP for a total ATP yield of 4 ATP. Well, that's okay, but gosh, that's obviously not where the most ATP is going to come from. So really, maybe what we need to understand that's more important is that something that's going on here is causing us to produce a lot more ATP in our final steps. So notice we have 32 to 34 ATP versus 4 ATP. Or if it doesn't even go into the rest of the cellular respiration, we can have 32 or 34 compared to 2. So obviously something's going on here that's really important. So what is it that's going on here? Well, as we say, each time we're breaking something down, we keep pulling hydrogens out of it, and we're turning NAD+ to NADH, and we're turning something called FAD into FADH2. There's 2 more hydrogens we pulled out. Now, notice I have 2 molecules of NADH, so that's really a total of 4 hydrogens. I have 2 molecules of NADH, 4 hydrogens. I have 6 molecules of NADH, so there I really have 12 hydrogens. Then I have 2 molecules of FADH2, so I have 4 hydrogens again. Now, again, just understand that the main thing we need to understand is we're pulling hydrogens out and forming these molecules in this thing called an oxidation reduction reaction. Okay, so what's going on here? Well, these are carrying the hydrogens to our last step. Everything else donated hydrogens, but now we're going to use the hydrogens that were donated to the electron transport chain, and we're going to come up with these totals. So what we want to look at next is actually what happened to the hydrogens once they got to the electron transport chain. So our next video will be about that.